Hello, everyone. Hi, this is Seogjoo from City University of New York, Queens College and the Graduate Center. So I've been running this workshop through the Initiative for Theoretical Sciences for some time. And this is the first in a series of workshops that we are going to run with the title of Machine Learning in Chemistry. There is no doubt that machine learning has become one of the frontiers in sciences and engineering. And application or the development of machine learning approaches in chemistry has been particularly challenging because of two particular issues. One is how to handle with relatively small number of data that you typically get in chemistry research. And the other thing is how to actually develop good feature space or data space that can represent chemical information and structure. And also beyond that, how do you really use machine learning to extend the capability of theory and computation? So I'm happy to say that we have four really frontiers in this direction of research that combines machine learning and chemistry. And with that, I want to first introduce Adrian Roitberg from the University of Florida.
Thank you, Sagi, and thank you, Johannes, for the invitation. Welcome, everybody. I'm going to try to tell you in a short time some things that we've been doing in my group for the last about 4 years or so, 4.5, related to machine learning in chemistry. And we have a very particular angle that we like to play with. So, as some of you may know, my past is in biomolecular simulations, and some of the things that we're interested in are modeling biomolecules, modeling docking and scoring, doing some things about drug design, usually or previously doing either classical mechanics or QMMM. And you can read this slide, but the idea is that when you do drug design or in general free energy calculations, as it turns out, we actually know the equations very, very well. We know the statistical mechanics on how, you need to compute. We know in principle exactly how to get very accurate energies and forces, which is what you need to do molecular dynamics or Monte Carlo, because we can do very high level quantum. The problem that one has when you do these things is that, so essentially we're set mathematically, conceptually, we're set to never do an experiment again, because we really need to do super sampling of configurational space and compute energies and forces very accurately. If we have those things, we're done, right? The problem is that those things are literally incompatible with each other. If you want to have a very accurate method historically, like coupled cluster theory, then you need to be willing to spend half a day doing a single calculation for a reasonably small system, and then we're going to get accuracy, but you're not going to be able to do something, right? If on the other extreme, you want to use a force field, which is classical force field, you can do huge systems, right? You can do millions of atoms. The calculation is very fast, so sampling you can do, but it's not super accurate, right? Or it depends very much on the system. So this has been historically this conundrum, right? That we, if you basically, if you want to be very accurate, you you cannot sample conformational space. If you want to get conformational space, you cannot be very accurate. So we set up to, I'm going to show you a method, but what we wanted to do is very particular. We wanted to have a system that will learn energies and forces. It's going to be a neural network, I'll tell you in a second, and it will be mimicking some level of quantum. So what I need to deliver to you, right, and you should hold me to it, is a thing that will show up in this quadrant on the top left, right? A thing that will be within reach of whatever it costs you to do a force field, so microsecond to sub-milliseconds, but it should be as accurate as some high level of theory, right? And in principle, we have our own, if I can deliver this, we have our own ideas of what to do this, but I think what's important for the field is what would people do with that, right? If you could break this balance. So just as a joke, right? This is the name. You always have to come up with a cute name for these things, right? And if you follow the red things, it spells Anakin because we're Star Wars nerds. And the idea is that, we're going to train a little Annie, a network. We're going to train it to be a quantum mechanical Jedi master. And when you're done, right, you're supposed to have that. And you all know what happens in the movies when you keep going, right? That Darth Vader shows up. We don't want that part. So how does it work? When you train when you are working with neural networks, there's or in any machine learning method, there's two stages: training and inference. Right? Inference means actually using it for prediction. In training, we get this little Padawan network that doesn't know anything, and what we're going to show them are pairs of structures for a molecule and their quantum mechanical energy at some level of theory. Okay, so this is the input data. I'll show you the details in a minute. Right? It's going to learn pairs. This structure has this energy. This other structure has this energy. Then, as any machine learning method, this thing will predict the energies for that structure. Clearly, it's not going to be any good because it has not been trained. And then you go backwards. And then what you do is you look at those errors and you train this network and you keep going until you reach a point where you're satisfied. And now you can move into inference, right? So now you have a grown-up network that you can use. And then the job of this network is you're going to feed it a structure. Think about the input of a quantum mechanical calculation, right? You're going to feed it atomic number, XYZ, that's it, right? And this thing is going to give you energies and forces. And what you do with these energies and forces, it's, we have our business, you have your own business, you can do dynamics, you can do whatever you want to do with it, right? There's a lot of possibilities. There is a crucial thing that we're doing that stopped the field from doing this for a while, and this is 100% kudos to Beller and Parinello, who came up with the idea that I'm going to tell you in 2007, which is, the problem is this: when you use neural networks, the issue is that your input network, essentially your data structure, when you start with, that you feed into the network, in principle has to be a fixed size, right? So when you feed a picture to Facebook, Facebook internally makes it 512 by 512 or some measure, right? The problem with this is that the molecules come in different sizes. Molecules don't like to be of the same size, right? So what Beller and Parinello did is said, let's do this, right? Suppose I have a space of things that have only carbon, hydrogen, nitrogen, and oxygen. Now you take any molecule with those elements, and what you're going to have, instead of one neural network that will give you energies and forces, we're going to have 4 networks. Each one of them knows only about one atomic number at a time, right? So the carbon network only knows about carbons. So if you have a molecule, you take the carbon atoms, you put it to the carbon network, yep? And what happens is this: in training, you know the molecule, you know the total energy, you go through the individual networks, and then we're gonna predict. Each one of them will give you a single number, which is the energy of that atom. All right. So now we're gonna write the total energy, the predicted energy, as the sum of those individual energies. Let's call them atomic numbers, but we can discuss that later. Then we're gonna compute the error versus the true quantum energy, and we're going to train the network to that. Okay, so each network knows about one atomic number, but they're clearly coupled because they have to, the sum of their outputs have to reproduce the total energy of the system. Now, immediately, you should ask yourself, how does the network know that that carbon is different than this other carbon, right? So in reality, what you do is you feed it a vector saying, I'm a carbon, but these are my neighbors. This is the stuff that comes with me with some radius of 5 to 6 atoms. Is that okay? So what the network is carrying is, I'm a carbon or I'm an oxygen, and this is my environment. And the environment of everything, almost every molecule that you do is going to be different for that carbon. So that's the way differentiates between carbon atoms, etc. And again, this was the big thing with that Beller and Parinello did early on. So now that we have this set, now we need to design data sets. I'm going to show you our first data set. We're now way beyond this at this point. Our first data set was very particular. We took every possible molecule, organic molecule that you can make that has a maximum of 8 heavy atoms. But by heavy, I mean C, N, and O, right? And then you put the hydrogens so chemists don't complain, right? And everything is peachy, everything is neutral, everything is fine. there's about 60,000 molecules you can make with maximum 8 heavy atoms. You can enumerate them. There's no more, trust me. And then for each one of them, we did quantum mechanics. And the way we did it is we locally optimized. The level of theory is some DFT level with some basis set, but that's not the super important part. You take this molecule, you locally minimize it, and then you start distorting it, right? For each minima, you do normal modes, you do temperature dynamics, right? You just mess it up, so they're not just minima. So we end up with an initial data set that is 22 million data points. So we have literally a data set that is structured, quantum mechanical energy at this level of theory, 22 million of this, right? And maximum 8 heavy atoms. We did the usual 80% of these, we fed it to the network to train, 10% validation, 10% testing, right? And you go through the training data set. And I can answer questions about all this later. By the way, right now, if you just Google Torch ANI in GitHub, this is all on GitHub, and we have tutorials and things. They're not perfect, but we're willing to help whoever needs help. All right. So let me show you the very first thing that we did. Again, I like to tell the story in historical terms that convinced me that maybe there was something here. I was in complete disbelief. I thought there was no way this could possibly work, and we can go into why later. But the first thing that we did is we took molecules with 10 heavy atoms, right? So by definition, this network has never seen these things because the biggest molecule it's ever seen had 8 heavy atoms. So we took 131, total, there were 8,200 pairs structures. We pre-computed the energy with quantum, right? Just to test against that. But then we took those structures and we fed it to the network, right? So what I'm going to show you here is this. It's going to be 8,200 points, all molecules with 10 heavy atoms. At the bottom is the total energy that comes from quantum chemistry, from the DFT high level, DFT level of theory. In the y-axis is going to be the prediction from the network, right? And this is all in kilocalories per mole. So these are big negative numbers. And that's what you get, right? So, the prediction is essentially you get an error of about a k-cal or 2 in the prediction. Now, we all know that when you have big access, things that look correlated may not be. So if you zoom in, right, you still get correlation. And if you look in there, these are the molecules that happen to be in that energy range. I hope people can see them, but I hope you understand, or you can see that, they're not the same family, right? They're things with 6 member rings, 4, 5 things that are not ring, right? So this is not the same set of molecules or same family. If you zoom in into just one molecule, right? This red one here, then again, predicted total energy in the y-axis, computed with quantum in the x-axis, and again, this thing is 300 kilocalories per mole. It's a big range, right? So if you look at the bottom, which is really where the interesting stuff happens, the correlation is almost perfect, right? Time-wise, the acceleration of this thing is after you pay the price to train this network, and this is a general network. In principle, anything with CH, N, and O, it should be able to handle it. Once you prepay the price, which we pay, the user doesn't, the network can go through about 70 of these things it went in 3 milliseconds, right? So we're talking about sub-millisecond per structure. And if you do DFT, depends on which program you use, whatever, but it's going to be, in the order of 10 minutes to do this. So the acceleration is substantial. So I hope, I promised you in the beginning that I needed to deliver a thing that was fast and accurate, right? And at least for the particular examples that I show you, right? And you should be skeptical. I was. I'm starting to deliver something like that. By the way, we've now gone way beyond those data sets. Now we have, we've gone all the way to coupled cluster. We have solvation. We have charge systems, right? We have systems with way more than 8 atoms, different elements, but we can talk about that later. It turns out that we train 2 energies. So it turns out that just for this sheer size of the data set, we can actually predict forces, right? So in here, the DFT forces are in the y-axis, and the network forces are in the x-axis, and the z-axis is logarithmic. So this is actually very narrow, right? The prediction of the forces, And I'm just comparing with two of the common semi-empiricals, just to give you a hint about where we are on this. By the way, the semi-empiricals work they're super fast, but they're seconds, right? So like small number of seconds. So we're still substantially faster. We can do frequencies, right? We can do the second derivative of the energy and the Hessian, and you can get, for some drug molecules and some tripeptides, predicted versus DFT. We get errors that are similar from what you get from DFT to experiment, 20 to 30 wave numbers, right? Again, we're refining this continuously, but the idea is that, again, we train to the energy and we can predict the first derivative of that very accurately and the second derivative very accurately, which is, it was unexpected to me. We can do torsional barriers. This is important for pharma, right? And for drug design, the idea is if you go around this torsion in the middle, what is the energy, right? And I'm not going to go into details, but just focus on one of these pairs. The orange one or yellowish is the DFT torsional profile, and the blue is the prediction from the network that was trained at that level of theory. The other pair is a network trained to a different level of theory, to coupled cluster, and a network trained to that coupled cluster, and it mimics that, right? So we can pick up the differences between those methods. This is a big data set. If you go over every molecule and every torsion that they have, and you look at the error versus true coupled cluster, right? Small means you essentially get the coupled cluster numbers. If you look at it, we are somewhere here. This is our best network so far, right? So this network gives you torsional profiles that are like 0.2, 0.3 kcals per mole away from, if you were to do super duper coupled cluster. So very quickly, we can do chemical reactions. These are thermochemistry. There's no barriers here, right? It's just reactants products. And this is a set from Steve Wheeler and Ken Houck, and we can predict these enthalpies of reaction to about a kcal per mole difference. And if you want to do that with quantum, you have to go, pretty high in basis set and whatever. So paying the price. I'm going to skip this for a second because we are running out of time. Let me show you just two things. This is a data set from Merck. They did this. They pick up the program. They ask us how to install it, and then they went and they get essentially roughly the same result that we do. That you can get about a kcal per mole in energy in delta H's, and you need to go pretty high in DFT to get that, and it's fast. This is worth. Let me show you. This is my friend Luciano Abriata from EPFL. He has this virtual way, essentially a 3D thing where you can control the molecules. And what I want you to show you is that he took these two methyl radicals, and now what he's going to do is he's going to make them closer. And what you see at the bottom is the energy computed from the network on the fly as he moves things. All right. So what you're going to see is that he has some energy. Now he gets them closer, and now this thing should make a bond, right? And now you're going to see that the energy just drops because you made the bond. Yeah? And again, this is so far a toy, but the idea is that you can use this, if it takes the molecules now in the opposite direction, nothing happens, right? So it's a thing that we're working on to try to do, or he's working on actually to do some teaching. Let me just show you one thing just to show, so we can do molecular dynamics for big systems, right? I'm showing you, I'm not showing you that this is accurate or anything, it's just capability, all right? And then the last one that I wanted to show you that I like this one, this is a whole bunch of carbon atoms in a box, right? At high pressure, high temperature, and running, this is the same network that I just showed you for the biomolecules, right? And you see that you make graphene-like things, right? And then you get defects in the graphene, which gives you curvature, and then you can get Bucky-like objects, right? And this is all work in progress that we're working right now. So let me finish. That's the group, right? This work was all started by Justin Smith, a fantastic graduate student that went to Los Alamos for some years, and now he's in Boston working with a relay, a pharma. And then Oles Isayev from Carnegie Mellon. And then these are the people that gave us money and support in many different ways. So sorry that I was a little bit late, but I can answer questions now or later or whatever works. I leave that to Sagi. And thank you for listening.
Okay, thank you. So you have about 10 minutes to ask him questions. By the way, at the end of all the workshop, so there will be also informal discussion session. So you can reserve longer questions for the informal session. But just now, if you have any question, you can ask directly. Okay. Yeah, Robert, Ramsey. Go on.
Hi, thank you for the very interesting talk. I'm wondering if this network has been applied to molecular dynamics yet. Like, has this been used to run MD simulations yet?
Oh, yeah. So that's what let me show you. That's, by the way, so this is the network. I'm one of the developers of the AMBER program. Some of you know this. So this is actually AMBER running, instead of a force field, running the network. Yeah. And I'm not, we're refining. We don't know. We know you could, that it could be done. We're in the process of figuring out if the results are good or bad or whatever, right? So I'm not ready to do that. Early things is that it's better than regular forces.
All right, thank
Okay.
you.
Yeah, Pablo Videla, do you have a question?
Yes. Hi, Adrian. Very nice talk.
Hi, Pablo.
I have a question. So, is this force field allows to break bonds? So, can you treat, for example, proton transfer dynamics with this force field, or
Okay.
you need to train the force field to do that?
Yeah, that's it. So that's a great question. So, and I like to questions like that. I like to separate them into two parts, right? It can, in the sense that this network doesn't know anything about bonds, right, or anything, right? It doesn't really know chemistry per se. So it can. The question is that, is it any good? And I skipped a slide, but basically we have done chemical reactions. These are dill solders with substituents, and it turns out that it works. But like you said, you have to retrain it. So you need to figure out what this network could not possibly know, transition states, right? Or at least the way we trained it. So what you need to do is generate a set of data that is close to the transition state of the reactions you want to look at, and then it learns very quickly. Yeah?
Thank you.
Okay, Daniel Dave.
Thank you for your talk, Professor. My question is also about the potential for using such networks in large scale and longer box size MD. In atomistic MD, we face this challenge of when the atomic number of atoms in the box scales quickly, the computational cost goes down and sampling becomes a problem. Do you think this would help solve, in some sense, the sampling problem as well without...
It's not so, and this relates. Christian Scharf also asked a question that I would like to answer now about the cost of these things, right? It's a weird thing. So for small molecules, this thing is maybe, I will say, it's about 50 times slower than a classical force field for very small systems. But for large systems, what happens is that this thing actually scales linearly with the number of atoms, because you can essentially, if you have enough GPUs, right, you can just take one of these atoms and just, send it to different GPUs, right? So the scaling up for big systems is actually better. We think we think that it's still going to be maybe about 10 times slower. So we're going to lose some sampling, which means you just have to be a little bit clever about how to do it. I wouldn't try to fold the protein with this, because classical forces are good enough, right? But to look at ligand binding, where maybe you need polarization or you need special things, that's what I think the niche is.
Okay, Mauricio Coutinho.
Thank you, Adrian, for
Oi, Mauricio, how are you?
yeah, talking from Brazil.
That's
So my
right.
question is, if you want to train a new element, is there a trick to avoid the combinatorial scaling, or do I have to build a completely new data set?
You have to create a new data set. So now, when we went from CHNO adding sulfur, fluorine, and chlorine, we had to kind of double our data size. Yeah. So we had 10 million things, and now we have 20 million. No, you need to go to the work. The good news is that the network can help you be clever about it. For instance, a sulfur is not an oxygen, but it's pretty close. Right?
That's what I
So
meant.
it turns out that once this thing learned enough oxygens, it learned to learn the sulfur stuff was very easy, right? Because most of it already kind of figured it out, right? How to scale from sulfur. So there's no secret sauce, but you need to feed it the data for the new molecules. Now, computationally, this vector space that we have, this entry vector, that scales very badly with the number of elements. It scales like the cube of the number of elements, right? So we are exploring other ways to do this, right? But back of the envelope, we can do 30 to 40 elements, and they fit perfectly fine on a GPU. So it's an interesting area of research, but I don't think we need it now.
Mm-hmm.
Okay. Next person to ask is Dayu Lu.
All right. Hello, Andre. This is very nice talk. And, I have a question regarding training the neural network potential. I think starting from the beta pair network that there is a cutoff region to define the neighbors. So how would that handle some of the long range interaction like Coulomb interaction?
Right. So you're perfectly right. So one of the things that Dayu is saying, just to be precise, if you take two water molecules and you want to compute the interaction between them, the moment these two water molecules are farther than about 6 angstroms from each other, the network essentially doesn't, one water doesn't see the other one, right? That's it. End of story. If you increase the cutoff size for the network, then the thing scales, the training and everything scales too bad. So one doesn't want to do that. What you do is long range. What we're doing is dispersion electrostatics, right? That's what we're missing. The dispersion, it turns out you can add it analytically. They're 1 over r to the 6. We know, this is 1 over r to the 6, but not the short distance, right? This is beyond 6 angstroms. So there's many set of parameters one can use, but that's the way we do it. Charges is a different story. So with charges, the network that I presented cannot do that, doesn't know about charges, right? So what we have is I didn't have time to show about this. We have a second, what we've been doing is training to dipoles and quadrupoles, for instance, right? And then assigning local charges to the atoms that best fit those dipoles and quadrupoles. Make sense? Right? So we say, instead of predicting dipoles and quadrupoles as vectors, I mean, we do, but we predict them through local assignments of the charges, and then you have to do some charge redistribution. We have to play some tricks, but essentially now we have charges, right? And those charges, you just plug them into a Coulomb or Ewald or whatever you want to do, and they are they're conformation dependent. They change with the atom, so they are at least they capture. The experts will disagree with me, but let me call them for a second polarizable charges in the sense that they respond to the environment. They're not fixed charges anymore.
Okay, that makes sense. So in this
Can you maybe you can ask more
Sorry.
question later. Johannes, you wanna ask?
Okay, maybe a really quick one since we are running out of time for your slot. So the parity plot that you showed between the predictions and the ground truth values is very impressive. But again, so you showed one afterwards where you compared with type binding DFT, for example, where you did have a couple of outliers. So one thing we kind of found quite rewarding is to actually look at those outliers, do a bit of pattern recognition. Did you ever have a look at which systems the predictions are worse than for kind of the standard accuracy?
In fact, so we use that. We have our own method. I didn't talk about this of uncertainty quantification, right? We have a way for the network to tell us when it's, it's not performing well or that we shouldn't trust it. So we actually use that to train. We basically take the systems where it's underperforming, we compute quantum, and we retrain, right? We do this, essentially flow-wise. We do continuously. There are usually, most cases, whenever it performs badly, we can look at the data set and essentially find that there's nothing even remotely close to it in the data set, right? So as long as there's something like it in the training set, it's performing well. When you go outside, you have troubles.
Right, so there's nothing fundamentally where, so it's basically a lack of training in a certain domain. It's not that there are certain molecules which have a particular nature that can't be captured.
We haven't seen that. I mean, there's certainly molecules for which DFT is not good, right? For instance, so, and this thing will mimic that, right? This thing is not designed to fix the functional. There's other people working on that. So there's places where it's going to suck against high-level theory, but that's the fault of the DFT, not the network. But no, we haven't seen, at least maybe we haven't looked enough, but we haven't seen obvious trends. No.
Okay.
Great, thanks.
Thank you. Mark Tuckerman, is your question short, or you wanna do it later?
Hopefully short. I mean, basically,
okay. Yeah, do
it's
it in 30 seconds, please.
okay. 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 Adrian, so let's suppose you want electronic properties, dipole moments, polarizabilities, and all that. Is it better to train within the networks you're already working with, where you get the energies and forces, just add these as additional things? Or does it make more sense that these be done as separate networks, that you simply evaluate, at the end when you want to obtain these properties? What is better?
I don't think, I think it's still an open discussion. We prefer doing it all in a single network because, it's just coming from MD. I like to have these properties on the fly, right? And essentially, self-consistent with each other, right? But I don't think there's anything in particular. Certainly, I wouldn't be, if you have a network that were great, just dipoles, and you run an MD with good energies and forces, and then you post-process with a network doing that, I don't think there's anything. I think that's perfectly fine.
Okay, yeah, thank you. Thank you, Adrian, one more time. Yeah.
Thank you, everyone.
So we have actually informal discussion session at the end of the workshop. So if you want to join, please do so. Next speaker is Christine Isborn from UC Merced. So we are going to turn the gear a little bit, and then she's going to talk about excited state and spectroscopy.
Okay, I think you guys should be able to see everything here. And I'll be building nicely off of what Adrian introduced here, taking a lot of those same ideas that are developed for figuring out a ground state energy and taking it to build up an energy gap, so between two potential energy surfaces. We actually are looking at a few different sets of electronic properties with machine learning in the group, and since this kind of group of people in the audience is interested in seeing what kinds of things we can do with machine learning, I thought I'd just touch on a couple of the other projects, because sometimes machine learning is good for speeding up your calculations so that you can learn new chemistry, and sometimes it can actually allow you to gain new physical insight as well. And so there's just a wide variety of applications that we can look at, and I've got 3 different things, all different interesting collaborations going on in our group, and I'll just introduce the 2 of them briefly before getting onto the main story. So on one project, I'm working with a colleague at UC Merced, Harish Bhatt, And we have an awesome postdoc, Prachi Gupta, and a grad student who actually started up this collaboration. And we're looking at electron dynamics. And what's really cool about this project is that we hope that it will lead to physical insight of density propagation. So things like exchange and correlation potentials and what those should look like in time. And for now, what we've developed is a framework where we can train with a delta pulse, where we do all of our training data, where we apply a delta pulse to the system, and then we propagate the electron density. And that's our training data to learn the Hamiltonian for this system. And we've got a variety of small molecular systems we've looked at so far. And then once we learn that Hamiltonian, we use that with any laser field parameters that we want. So what's just shown here is one bit of information of different elements of a density matrix for ethene, where we're doing TDHF 6 through 1 plus G star propagation. And the training data is all without the field. But then here we've applied a sinusoidal field, and we see how the density matrix responds, and we're able to get that predictive capability. And so this means with one set of training data, we can explore a whole realm of different pulses. And then what we find more exciting about this is now that we have this machinery to learn a Hamiltonian, we can go to higher levels of theory and think about what's missing from DFT, what can we put in there to get things even more accurate? Can we use machine learning to actually do some equation discovery to learn about these potentials? What's a delta pulse? A delta pulse is just a really quick field, and then you turn it off and you propagate without it. And that allows all the resonant frequencies of the system to mix in. And so at this point, we've got results for a variety of systems, and we've got the kind of system setups. Prachi's extended it to bigger systems. Karna's looking at a bunch of different pulses, and we're pretty excited about this project. And another project where we're looking at charge transfer, and this relates a little bit more to Mark Tuckerman's question. I'm working with my colleague at UC Merced, Liang Shi, and it's grad student, where we're looking at water as well as trying to capture charge transfer in water. So we can do that with quantum mechanical calculations, where we do these small little clusters. And what we're doing is mapping that onto learning the charges so that we can predict electronic properties of bulk water. Can we model the dielectric constant of bulk water by mapping quantum mechanical charges of water clusters that we get from sampling across this bulk? And can we get other electronic properties of water? And so what's shown here is some calculations that Bowen did on bulk water, where he's basically done QM calculations to figure out what are the charges on each of the water molecules, right? Any one water molecule is not necessarily neutral like we see here. There's charge transfer depending on individual configurations. And so we can map that kind of distribution of charges that we get with all these water molecules in the bulk system, and we can develop a neural net. In our case, we actually did better with kernel ridge regression than with the neural net. And from that, we can predict all these charges on water. We can simulate a water box with an force field to get all those configurations, right? Water has been studied for a long time, and we get the configurations really well with fixed point charge models, but we don't always get all the electronic properties, right? So the idea is to use these configurations that are very good, but then learn the dipole surface, learn more about the charge transfer and polarization. And so if we look at the spectrum of water, TIP4P misses one of the peaks that's thought to be due to charge transfer and polarization of water, because it doesn't have that built into the model. But each of these different machine learning models that are built on different DFT functionals is able to get this peak in the spectrum correct, because it's getting some of that charge transfer and polarization. So now we're looking at which functional and atomic partial charge method makes sense. Some of the methods that you are used to thinking of as being very good, like CHLG and whatnot, don't work well when we have large QM regions. So we had to abandon those and think of things like iterative Hirschfeld instead. Okay, so now I'm getting on to a story which is a piece of my collaboration that I've had for quite a while now with Tom Marklin at Stanford. And then we had an excellent postdoc in my group. Tim Zulsdorf was working on this for a while as well. He's now an assistant professor at Oregon State, doing some pretty awesome spectroscopy stuff. And Michael Chen, Tom's grad student, is the one who's done all the machine learning work that I'll be talking about. And what we're looking at in this project is learning an energy gap. So same idea of learning a ground state energy, all the atoms contribute. Now we want to learn a gap between a ground and an excited state surface. And the idea is that we want to get energy gaps as a function of time. So we'll be running some molecular dynamics simulation with a cheaper method, although maybe with what we're kind of talking about here, eventually the machine learning method and the gradients are going to enable the fast quantum mechanical quality long time scale MD. We hope we get there. We're thinking about that too. But what we want to do is get these energy gaps as a function of time. As the system is vibrating and interacting with its environment, the energy is changing. And we want to predict that quite accurately in order to take these energy gaps as a function of time, build up correlation functions, and then model optical spectroscopy. So what I'm showing over here is the photoactive yellow protein, and it's a density difference. And what we see here is that this chromophore that's in the protein, there's a lot of density difference there. That's clearly where the optical excitation is happening between the ground and excited state. But you also see the environment, part of the surrounding residues contributing to the density difference. So rearranging in response. And we want to capture that environmental response, not just the chromophore part of it, in our energy gaps. And here is just a movie of that same chromophore of PYP in water. This is the system that's going to be our benchmark for most of the talk, this chromophore in water. It's an anion, it's strongly hydrogen bonding to its environment. And we want to take all of that information and use that to, let's see if the movies want to work. Model things like two-dimensional electronic spectroscopy, where I'm pumping and I'm probing and I'm seeing how the excited state dynamics or relaxation on the excited state surface evolves in time. So this is kind of our goal here, is to model this by having accurate enough energy gaps. Okay, don't freeze. All right, here's my math slide that kind of sets things up, and I'm trying to put here the context of what we're doing with our energy gap formulation in the context of other methods that you've seen before. It's not exactly related to machine learning, so I'll go through it kind of quickly. The idea is we want to compute a linear response function. You can compute your absorption spectrum in the inhomogeneous limit with an ensemble approach, where I do that maybe MD simulation and I have many of these excited state calculations and I sum them all up, but they can be independent in time. So this is a static approach where I'm sampling over configurations. The machine learning I'll talk about today would be suitable for this, but it'd kind of be overkill because what we want are tens of thousands of these energy gaps. And we don't need tens of thousands here. We might need 100, we might need 1,000, depending on how we choose our configurations. Alternatively, you might be more familiar with making the Condon approximation and computing a spectrum with a Frank-Condon approach, where we're computing normal modes and you get these vibronic progressions. The approach that we're looking at uses a cumulant expansion of our linear response function. And that means that we're kind of building our linear response function from correlation functions directly. And what's very appealing about this approach is it gets all of the vibronic progressions that you get from a Frank-Condon approach, where you've got the vibrational motion of your system coupling the ground excited state with all of those environmental effects that you get with an ensemble approach. So we're treating the vibrations of the system and coupling to the environment on equal footing here. And I like this picture that shows things, it's a recent ChemRev article that shows how once we compute these correlation functions, we've got these fast oscillations of the chromophore CC stretches. We've got these slow oscillations of the environment, in this case, like a protein environment. We Fourier transform our correlation functions and we get this spectral density. I'll be showing more spectral density plots, so it's sort of nice to set this up. in the low frequency region, we have that environmental response. And then in the high frequency region, we've got the CC stretches and whatnot that couple strongly to your optical excitation. And what you really have is kind of a convolution of these different degrees of freedom in your resulting spectra. Okay. So just outlining the method that we're kind of using to compute the optical spectrum, we're going to be computing these energy gaps as a function of time. Then we need to compute a correlation function, and then we plug that into our line shape function, maybe with the appropriate quantum correction factor. I saw Pablo here that we use some of his when we go up to third order terms that I won't be talking about today. But once we have that, we can plug that in and we get linear absorption spectra, but also very appealingly, we get these nonlinear absorption spectra and emission spectra as well. So we get nonlinear spectroscopy once we build these correlation functions. So we're going to get interactions with the environment, vibronic couplings, linear and nonlinear spectroscopy, but as you might imagine, computing tens and thousands of these energy gaps is very expensive. This is a problem that is ideally set up for machine learning. I want to learn one system in its environment. I'm going to have to generate some samples, but then once I learn that energy gap, I can do a classical MD propagation or maybe get to the machine learning propagation, and I can statistically converge my correlation functions. I can go up to higher order correlation functions. This will be a pretty key approach to anyone who wants to use this approach for spectroscopy in a complex environment. Okay, so that's motivating what we're doing here. Now, kind of just setting the stage in terms of computational time that we've spent for these calculations. So this approach that we're advocating for does well. We can apply it to any system. So whether or not you have strong or weak coupling to your environment, you can apply this approach and you get these multi-dimensional spectra. Okay, so let me just give an outline of how much the calculation takes in terms of time. So for this PCT, that's the name of the chromophore photoactive yellow protein. We stick it in water. We want to treat the environment accurately. So I'm actually treating the water at the quantum mechanical level. So we've got a full salvation shell, a little bit more. So 500 atoms in our QM calculation. We do a TD-DFT calculation of the energy gap. I'm using Teracam, so we're actually using GPU acceleration to make those calculations feasible. Each of these excited state calculations might take 8 hours or so, right? Depends on the GPU card you've got. We've got to do on the order of, let's say, 32,000 of these to get our correlation function. So this is a lot of GPU time. Nobody wants to wait around 29 years. Obviously, we can run many of these calculations in parallel, so we don't have to run them sequentially, but it's still a massively computationally heavy problem. Can machine learning help? The answer is clearly yes. I wouldn't be invited to give this talk otherwise. So here's some of our details here. Same idea. Our energy is a sum of contributions from each atom in our system. In our case, Tom found that these Chebyshev polynomial descriptors worked quite well. It's a combination of radial and angular polynomials of a given order that you decide what order you want to go up to for how many descriptors you want in your network. And so we do that for a given atom, very similar idea. And so our descriptors are G, and we're going to use this kind of color scheme here to separate our chromophore atoms, our system, from the environment. And we're going to use our chemical intuition to think about how to build this neural network in a way that's computationally effective to think about those environmental effects that we think are very important. Okay, so this is just a picture of a brute force neural network that we might use. Each atom in our system, we build a descriptor. For that, each one would contribute a piece to the total energy gap. So this U is a gap between the ground and excited state. We're training with thousands of TD-DFT energy gaps in explicit solvent. And so red is the chromophore, blue is the environment. What see though, if we look at the density difference, obviously not all of the atoms are contributing to the excited state in the same way. So we should use our chemical intuitions to build our network a little bit differently, right? Most of these solvent atoms are not contributing very much other than a little bit of electrostatic polarization, but, and some of the chromophore matters more than others. So what we did was think about which atoms should be in our system. Here in the method I'm kind of highlighting is an indirect solvent model where the atoms of the solvent are not directly contributing to the energy gap, but they do contribute to the descriptors that we build from the chromophore. So right when we're doing this, we're figuring out all the atoms within a given cutoff distance and building the descriptor here. So these are contributing to the descriptors for the chromophore atoms. And you can decide, should hydrogen bonding waters be part of our chromophore or not, and build accordingly. We also built a hidden solvent model that doesn't take any solvent model atoms into account, but it sort of just is built into the energy gaps that we're training with. And I'll go over some of this kind of quickly so that we have time for discussion. But our errors as a function of training set size, you can see that for small training set sizes, our brute force approach is not very good, even though it has more information. We need a lot more training data to make it more accurate than the hidden solvent model. Whereas this indirect solvent approach gets better and better, and it doesn't need as much training data as the direct solvent approach. So we think this indirect solvent approach gets most of the relevant physics. And you can see that here. These are the linear absorption spectra and the spectral densities. When we use this hidden solvent model, the goal spectra are these filled in gray ones that we get with the full TDDFT calculations. We get a good, okay shape, but we don't get the right broadening. And that's because in this low frequency region, we don't have the right response of the environment. But as we add in the indirect solvent and the direct solvent, we get that response correct, and then we get the right line shape. It does come at the cost of more training data. And then here is our 2DS results that we get when we go to nonlinear optical spectroscopy with the hidden solvent model, not quite matching the reference. But then, let's see if I can advance past the movie stage. If we compare our indirect solvent model to the full TDDFT calculations, you can see that the spectra are qualitatively, if not quantitatively, the same here. And so that is getting us pretty close to where we want to be with converging our correlation functions. And this is just a summary on the next slide, if my movie will stop, of the 3 different solvent models that we've built in. Oh, actually, I only showed 2 of them, indirect and hidden here compared to the reference. And you can see that the indirect gets something very close to the right Stokes shift, and so has the right physics built in here. And I was going to show data for another system that had weaker interactions for the solvent. I won't really spend time on it, though. It's the same kind of general picture, but we can use the hidden solvent model and get things done even faster if we have weak interactions with the environment. Yeah, I think I'm close to being out of time, so I'm just going to flip through here and give you the punchline, which we think this is one of the best things to do with machine learning. If you want to compute correlation functions for optical spectroscopy, it is an amazing tool. You are going to save a lot of computing time if you go through and use this approach. And now we're thinking about how to use transfer learning to maybe go past TDDFT. So similar themes that we've been thinking about. We're looking at more complex systems. So doing machine learning for a full protein, we think that's going to be possible and is going to be an exciting new realm to think about. And overall, it's been a really fun collaboration with Tom and his grad student, Michael, and with Tim. I think we're doing a lot of cool science. I'm excited to see where it goes next. So I want to thank them for being great collaborators, and thank you all for your attention.
Thank you. Okay, so if you have any questions, please raise your hands or send a chat to me. Okay, Pablo.
Hi, Christine. Thank you very much for the talk. So I have a question regarding I know that you have different models for the solvents, and probably this question doesn't apply for the hidden solvent, but if you were to change the solvent of your system and you want to predict like a stock shift, for example, do you need to retrain the network with new solvent simulation, or the network somehow knows that the effect of the solvent is kind of electrostatic in nature and can predict different solvents without training?
How we've built it is not as general. It's not going to be transferable to different systems and different solvents. It really is so that we can do one system in one solvent. So it's not going to work for like, oh, here's one molecule, let's apply it to a bunch of different molecules and a bunch of different solvents. We would need to do a little bit more training. That said, it seems like once we train on one system, things are very transferable. I don't think you would need to do too much training for another solvent. You could probably get away with very few snapshots. Once you train on one solvent and get things good, you could probably train on very few snapshots to update it to a different solvent environment. And I haven't shown our most recent results where we're looking at adding gradients to things, but that seems to be a very powerful way to just use on the order of possibly 20 or 50 snapshots for training.
Thank you.
Mm-hmm.
Okay, so let me ask one question. How do you actually, Johannes? Yeah, you want to ask first? Okay.
Quick question. So you mentioned at the beginning one example where your KRR worked better than deep neural network. So what kind of kernel did you use, and do you have any explanation of kind of the difference in performance? Any insights? Do you have a look?
I don't have a lot there of insight yet. It's a fairly new result. So that was in predicting the charges on water, the collaboration with Liangxi. The KRR prediction, the error is a little bit smaller and it definitely trains a lot faster. I don't have a lot of insight. Leon might be on this call. I don't know if he wants to jump into the chat and answer a little bit more about that. But it seems, you know, some things the neural network works great, but sometimes you're like, do I really need 3,000 descriptors for this crazy polynomial? Maybe I can get away with something where the applied mathematicians have already figured things out and I don't need to go there. And so we've also seen that in the project with Harish, where we're just like, we don't really need a neural net. Let's just use some linear regression here. Yeah,
no,
so
that's all fine and okay. So I mean, did you pick any particular kernel which would support kind of the problem that you model? Is there any particular physical insight that went into selecting the kernel?
No, not in this case. No, I think we were just kind of trying a bunch of different things. But if you have suggestions for what might work specifically for that,
no. So I'm all for trying out different things.
Okay, yeah. This is
so
kind of where, like, a lot. I feel like a lot of machine learning is this, right? Where you're just like, let me turn all the knobs and the dials and see if I can get the error down. And so that was one of those things as well.
No, and so yes, I'm completely on board with that. And so we do auto machine learning where we basically automatically try out a lot of different things. And but it's interesting to go back. So once you find something, in particular when you don't necessarily observe it, so I mean you definitely expect that you have a smaller footprint in terms of the data need when you do the KRR compared to a neural network, at least a deep one with some decent featurization. But yes, so sometimes you can see, I mean, so for example, if your kernel resembles, for example, a Coulomb potential, right? So you're basically building in certain physics into the kernel. And so I mean, that might help you. Anyway, so sometimes it's interesting to have a look at why these things may happen. So sometimes if you've got inherently linear relationship or multivariate linear relationship, right? So I mean, you get away with having a very simple model. You don't need to have the heavy hammer of a DNN. So it's sometimes interesting to go back. But again, so sometimes you don't actually see anything.
So what was the reason? I mean, so what was the main benefit of using Chebyshev polynomial? Have you tried any other?
In this one, that one worked well. In actually the other project, about the charges. We found that the Bell error functions worked a little bit better. The error was slightly smaller than with the Chebyshev polynomials. And so, I'm not quite sure. Again, this is one of the things that I feel like I don't relate this to physical insight. Like, I don't know why this descriptor works better for this particular property. It did seem like we didn't need quite as many parameters there, though. So at least that made it a little bit more robust.
Yeah, and also related question is, how sensitive are the line shapes compared to, for example, spectral densities? So for example, I think you may also try a series of other spectroscopic data, not just line shape, right?
Yeah. I feel like the spectral density is like our most insightful tool, right? We're using that to build all these other pieces, but we get to really zoom in on which peaks are overemphasized and underemphasized, and we can look at the low frequency region and use that to be like, oh, we're missing this environmental effect in our network. We need to add in, actual kind of contributions from this part of the environment to get this low frequency region, right? I feel like because there's so much data in the spectral density that getting that right is going to tell us if we're going to get all the other features right.
Mm-hmm. I think probably there are other questions may take a long time, so they may be waiting for after the workshop. Okay, so I think it's time to thank again Christine for wonderful talk. And also, I also want to introduce you to Johannes Hachmann, who is co-host of this workshop. He's from University at Buffalo SUNY, and he will be in charge of the rest of the workshop.
Great, thanks so much, Sergey. So yeah, it's my distinct pleasure and delight to introduce Coley as our next speaker. So he's an assistant professor at MIT, and he's doing some of the most exciting research that's currently going on in AI and machine learning guided synthesis prediction. And so I don't want to take too much of his time. So Connor, please take it away.
Thanks so much, Johannes, and for the invitation to be here. So like Johannes said, I'm Connor Coley. I'm an assistant professor at MIT, mostly in chemical engineering, but with a shared appointment in EECS as well. And I'll be talking a little bit about the work that we do related to accelerating molecular discovery with an emphasis on drug design. So I'd like to start off with a sort of big picture philosophical discussion of, what is discovery? How do we approach discovery? What's the process that we use to identify functional molecules? And in almost all cases, we end up with an iterative process. We end up with this workflow where we have the design of the molecule that we'd like to achieve in terms of its properties, right? For a drug, we'll define some target bioactivity, toxicity, solubility, all these different multi-objective functions. With that goal in mind, we'll design models and beliefs that try to predict for new molecular structures what properties they'll exhibit. We try to generate then hypotheses, right, of new molecular structures that we think will achieve the design criteria. The ground truth for everything that we do is experiments, and so we have to validate those predictions through chemical synthesis and testing. Usually that's going to give us new information from those assays that we feed back into our models to make them more accurate. As we churn through this cycle, maybe after hundreds of experiments or thousands, we might come across a molecule that achieves all the criteria, right? It checks all the boxes, and we'll call that a discovery, and hopefully we advance it to the clinic. So what you think about is really accelerating this process, accelerating the process of discovery by bringing in computation. Where computation means data science, it can mean machine learning, it can mean robotics and laboratory automation as well. And we do this both in terms of accelerating the generation of hypotheses as well as accelerating the testing of those hypotheses. And what that ends up meaning in a very practical sense is the design and synthesis of new molecules. And we're going to focus on those two aspects for this sort of overview of our work. So this belief part is really important, and these types of models that correlate structure to function are really a cornerstone of drug discovery and of most forms of molecular discovery. Right? We very often want to correlate structure with function in order to predict the function of untested molecules. And so in the sort of more classic feature engineering approach, the typical workflow might involve taking a molecular structure, describing it with some set of descriptors or fingerprints, right? A numerical representation that captures aspects of that molecule. And then we regress, right? Then we learn how to correlate that numerical description to some function of interest. This could also be energies and atom level forces, of course. Now, there's been this sort of nice shift towards a more representation learning approach where perhaps we don't have to pre-specify the descriptors that are important. Perhaps we can show these models the raw molecule, right? Just the structure of the compound, and we can let the models pay attention to the specific aspects of molecular structure that are important. And in this view, we still end up going through this numerical representation as an intermediate, but really we try to learn end to end from structure all the way to some labeled property. Now, I don't want to dwell too much on this slide because it's sort of an overgeneralization, right? But I typically think about building these surrogate machine learning models as in two camps, right? When we think about fitting machine learning models for molecular design on experimental data, often we're trying to take these data sets of things like bioactivity, where we might have hundreds or thousands of data points. We're trying to then extrapolate to new molecular structures for which we don't have labels. And these are settings where we don't actually have good simulations, I would argue. We don't have good first principle simulations of these properties. And so we're quite reliant on data and our ability to generalize and extrapolate from that experimental data. When we train on simulated data with these surrogate models, we can do all of the really, really cool things that we've just heard about from Adrian and Christine. Right? We can accelerate calculations by orders of magnitude. We can leverage our ability to simulate systems, either ground state or reactive systems or excited systems. We can apply them to much larger research questions than if we were stuck with the full cost of the calculations themselves. So we sort of have surrogates for data as well as surrogates for computational results that let us leverage them to ask interesting questions. But both raise this question at the bottom in red, right? Both require us to represent molecules as objects for neural networks if we use neural network methods. They require us to represent molecules numerically at the very least. And there's a huge number of choices, and we just started getting to that in the discussion at the end of Christine's talk, right? There's a lot of different ways you can try to model these systems quite often. When I think about this task, I think about dividing up the techniques in terms of the information we're trying to capture. So if I just care about molecular identity in terms of its one-dimensional structure, I can use techniques like one-hot encoding. Can't generalize, but that's maybe okay. With one-hot encoding representation, you can use a number of different machine learning techniques and regression architectures. If I want to capture the two-dimensional connectivity, maybe I use a graph representation. If I want to try to capture a little bit more, I could try to think about using, I don't know, an image or a drawing of a molecule. It's a little funny, but people do that. I can represent molecules as strings using the SMILES notation. Right? That's another valid way of representing them for modeling purposes. And as we heard, especially from Adrian, right, if we're thinking more explicitly about three-dimensional conformations and specific explicit coordinates, right, we'll use atomistic networks where each atom has a set of Cartesian coordinates, and we learn off of that kind of representation. So there's a whole zoo of approaches, and yes, we try a lot of them, but we do quite like graphs here at MIT. So our bias is certainly towards graphs. I'll briefly highlight a recent preprint we posted, which is trying to think a little bit carefully about this question of molecular representation by addressing some of the edge cases that existing techniques sort of ignore. And I guess to call stereochemistry an edge case is not doing it justice, right? A lot of molecules have defined stereochemistry, and it has a huge impact on its properties, especially in biological applications. And so when we think about modeling molecules with stereochemistry and we use these three-dimensional representations, we have to be quite careful about whether we actually can describe chirality. Right? So chirality is this property, these two enantiomers where one is a mirror image of another. And if we use families of neural networks that are what are known as E3 invariants, E3 invariant means that the network is going to be insensitive to translations, rotations, and reflections. So if I have two enantiomers, they're two different molecules, they have two different sets of properties. But if I use an E3 invariance network, which are quite common, I can't actually distinguish them mathematically. I'll get the exact same prediction. SE3 invariance is a special Euclidean group in 3 dimensions, and this helps solve that. So we can tell enantiomers apart. But this raises some other questions as far as, well, if I have a bunch of different conformers of the same molecule, does the model think it's one molecule or multiple molecules? Right? Can we teach models to understand conformational flexibility and stereochemistry at the same time? And that's the subject of this preprint that's linked at the bottom, where we build a new type of invariance, equivariance, into a neural network such that the model mathematically treats conformers that differ by rotatable bonds identically. So we can tell enantiomers apart, we can have arbitrary rotations around single bonds, and the model treats them the same, the rotatable bonds, I should say. And so we do this kind of work in property prediction, but we also think about the applications to molecular design and synthesis. So I do want to make sure we give enough time to that. I'll briefly just highlight here a nice figure from Alain Asperguzik. So many of us might have heard about generative modeling and this notion of inverse molecular design, right? We can take property prediction models and we can screen candidates against them in this direct approach. But we can also ask models to generate new molecular structures, right? We can have GANs and VAEs and all these different types of models propose brand new structures that have never been reported. These are very fun, they're very exciting, but they have some pretty bad failure modes. So in particular, a lot of these methods, when we ask them to optimize some black box oracle function of interest, they won't know anything about synthesizability or even stability of molecules. And so you can use these methods that are achieving state-of-the-art performance on baselines computationally and get molecules like the ones on the slide. It doesn't take too much chemistry knowledge to recognize that this structure is not something that you would give to a chemist and ask them to test in the lab. Right? This very long chain of oxygens and nitrogens, this is not something that you could ever produce. And yet these models are very earnest in recommending them, and sometimes they look good based on computational benchmarks. So clearly something's wrong. And we could tell something is wrong if we thought for a second about what it would take to actually synthesize these structures. And so that's really where a lot of our research comes in. We think a lot about chemical synthesis and chemical synthesis planning. So if we want to make a molecule, we need to know the recipe, right? If we want to make some target product compound here, like palbociclib, we need to know what starting materials to use, what conditions to use, right? How we chain together reaction steps in order to produce that structure. And so humans have been doing this for decades, and we're quite good at it. We broadly, not me, I'm quite bad at it. That's why I work on these programs. We need methods, right, that take this product structure as input and suggest or recommend all of the starting materials, all the pathways, right, everything about this recipe. And so we build models that facilitate this kind of computational thinking. We build models that replicate the act of retrosynthetic analysis and this sort of recursive simplification from the product to starting materials. So there's a few different tasks that we think about, and I'll be very brief here. But in addition to retrosynthesis, which is just the act of going from your product backwards to starting materials and building a synthetic tree, we worry about things like conditions, right? We worry about the details of how you would actually achieve a proposed reaction. If I think I can make A using molecule B and C, and I go to the lab, I'm gonna have to pick a solvent, I'm gonna have to pick reagents and catalysts, right? There's a lot of precision that needs to be there in the recommendation for this to be an actionable suggestion. Then I might want to know what I expect to produce. So I might want to anticipate, well, if I actually go to the lab and I mix B and C under these conditions, what do I think will emerge as the product, right? This forward reaction simulation is another task that we build models for. So all of these tasks and many more can be trained on data, right? We don't have good first principles methods, broadly speaking, for simulating arbitrary organic reactions. And so we instead look at the millions of tabulated examples that exist. We look at databases curated by folks like Elsevier or Chemical Abstracts or NextMove software. And we think about building models that analyze the patterns in the reported reactants, products, yields, catalysts, right? All these different correlations to learn what chemical reactions are possible. There's a lot of information that we don't have to learn from. And I could spend an hour talking about what we don't have to learn from. These databases don't actually give us concentrations or mechanisms or byproducts or failed reactions often. But nevertheless, right, we do have access to information about reactants, products, and conditions. And so we build models based on the data shown in green. And the subtleties of chemical synthesis are sort of open challenges that we're still working on. So it's one example of a model that we've recently built and released. This is a graph to sequence approach for retrosynthetic planning. So retrosynthesis is trying to take a product molecule as input and output reactant molecules. And in this formulation, what we wanted to do is take advantage of graph representations and graph encoders, which can be very effective ways of perceiving molecular structure. And so we have the graph as inputs, right, to this network. But then we switch halfway through to a sequence decoder. So we use a transformer style attention to encode the graph and decode to a string, to a sequence. So we decode into the SMILES representation of molecules, the SMILES that would describe the reactants in this case. And so we can benefit from the strengths of these two different types of neural architectures by stitching them together and having them do this translation task for us, right? Do this process of retrosynthesis for us. In the forward direction, here's another example of a study from a few years ago now, where we looked at a graph representation to try to predict the products of chemical reactions. So if we're thinking about chemical reactions that are not elementary steps, but rather, A plus B goes to C, as a chemist would publish in a paper, we can think about the reaction as the rearrangement of bonds in a molecular graph. And so what we can do is we can train a graph neural network to predict those changes. So we represent everything that goes into the flask, all the reactants and conditions, as this one big molecular graph with disconnected components. We train a message passing network, a type of graph neural network, to learn which bonds are likely to break and which bonds are likely to form. It can understand the reactivity of different functional groups in this manner. We enumerate possible combinations of those bond breaking and bond forming events. Then we can rank again. Now, so end to end, what this looks like to a chemist practitioner is that you provide the reactants and conditions as inputs, and as output, you get a probability distribution over the possible product species that could emerge. We're trying to formally predict the major product of a chemical reaction, but we get a full distribution over different ideas that the model thinks is plausible. Again, this can be trained directly on experimental data. Right? We can try to abstract away the patterns of reactivity from these databases of hundreds of thousands or millions of published chemical reactions. So we've spent quite a bit of time building and maintaining a piece of software we call ASCOS for data-driven synthesis planning. And so for this, we have a tool that essentially takes only seconds, sometimes around a minute, right, up to a minute, to generate a network of suggestions of possible synthetic routes. And so here, every one of these options in this big tree gives us a different idea of how to produce this target drug substance that we provided as input. So we have hundreds or thousands of ideas for how to make this structure. And each one is associated with some idea of the conditions we could use as well. Right? So we provide the recipes and a lot of ideas of recipes. This extends to more complex structures. So these tools do work for longer pathways. Right? This is a structure where it took 1 minute to come up with a 13-step idea. There's no guarantees about this being a good pathway or the best pathway by any optimality metric, but it's an option. The model can assess the feasibility. It can predict the likely points of failure. It can try to estimate the cost of starting materials. And it's something that a chemist can then take and review and refine. Now, these multi-step plans, again, they're not guaranteed to work, but it's been shown for both data-driven systems on the left and expert programs on the right, that the pathways produced by these models can be of comparable quality to pathways that you find in literature. So both of these studies, first by Marvin Segler for a data-driven system, and then by Bartosz Drabowski for an expert system, showed their suggested routes to a panel of chemists compared to literature routes for the same targets. And in both cases, there was no statistically significant difference in the preference towards the pathways. So experienced chemists couldn't actually tell apart the recommendations that came from the model from the recommendations that were actually known experimental literature pathways. So these tools are really at an interesting inflection point where there's a lot of opportunity to apply them, right? They're coming up with recommendations that are actually quite useful. I'm going to skip over the discussion of our experimental validation in the interest of time, but I do want to talk about how this comes back to intersect with generative design and de novo generation. Okay, so I talked about how generative models can propose absurd structures, right? They're silly, they're not stable, they don't make sense. Well, what we can do is we can take the recommendations and we can throw them through our model, right? And in seconds, we can get a quick check if it looks like they're easy to make or if they're hard to make. So we can use the synthesis planning programs to triage or prioritize the recommendations from these models. Now this works okay, but it doesn't work all the time because it could be the case that every single recommendation from our model is not synthesizable. That happens for some objectives, right? The model just proposes crazy looking structures and nothing it proposes passes this filter. So another class of techniques that I'm incredibly optimistic about, and this is a field that was helped sort of established by John Bradshaw in the last couple of years. And we recently posted our first foray into this category of approach, is we reformulate the process of molecular design as the process of synthetic tree design. Now this is, I think the subtlety here is important. So instead of optimizing a molecular structure by changing atoms and bonds, we optimize the molecular structure by selecting building blocks and reactions. So that every single molecule that these models are capable of proposing, it proposes via the construction of a synthetic route. So in a bottom-up direction, it learns to pick building blocks and pick reaction types that when you do the forward simulation produces molecules of interest. So it's this bottom-up approach that then lets us query the model with the target compounds. And in 1 second, in this case, we can get a pathway to produce it, even though it's dissimilar to the training data. We can use this for optimization as well. We can now optimize the molecular structure, but again, forcing the model to pick commercially available starting materials and valid reaction types. And we get these molecules that do quite well on performance benchmarks. So here we're optimizing some surrogate oracle function, GSK3 beta bioactivity. And we get a high scoring molecule that is so much simpler and so much more synthetically accessible than the other models, right? We force it to think in terms of synthesis. And so the molecule that it finds can be made in one step through a simple Suzuki coupling. So by forcing these models to think about synthesis, there's sort of this regularization that keeps them simple, keeps them small. It also keeps the recommendations actionable. That molecule is something you can give to a chemist and say, please make this and test it. The ones on the right, again, I have no interest in trying to make these, right? They would not pass our filter. So I think about 20 minutes, so I'll quickly try to wrap up, zoom out a little bit. I am very interested in autonomous discovery. I think a lot of the pieces are there, right? Machine learning and automation enter this workflow in various ways. Certainly the synthesis is something I feel very strongly about because we can't test molecules that we can't make. And so we shouldn't design molecules that we can't test. And there's a whole lot more work that can be done in this space. And so to very briefly summarize, this is a quick preview of how we can use these kinds of tools to evaluate molecules, propose new ones, and plan how to synthesize them. But we can still think about ways to merge these kinds of data-driven approaches based on experimental data with simulations, right? Merge our first principles understanding of chemical reactivity and chemical function with this kind of approach. Domain expertise also has a huge role to play in making our models more efficient. We want our models to be sample efficient and work in low data settings. Those are the most interesting ones. And really, experimental design is an area that we can talk about some other point. But the point of doing all of this, right, is that the bottleneck for discovery should not rely on intuition, right? You shouldn't have to have decades of experience in medicinal chemistry to design a drug. We want to shift the bottleneck, right, and reallocate human creativity to thinking about other problems. So hopefully we can have these kinds of systems design and test molecules a little bit more autonomously. So I'll thank everyone who I've collaborated on in this space, and thank my research group, as well as generous funding in particular from the Machine Learning for Pharmaceutical Discovery and Synthesis Consortium. So really looking forward to the discussion now and also after Brett's talk.
All right, great. Thanks so much, Conor. That was very exciting and very inspiring. All right, so I'll open up this talk for discussion. I would like to get started. I think Brett had a question in the chat. So do you want to ask that one directly?
Sure. Yeah, so I think it's very exciting, especially the last direction you were emphasizing about making them sort of consider synthesis built into the model. The way around that, and I think you looked at this in your paper, is to maybe if you used a synthetic complexity score as an auxiliary learning task. So how effective is that if you try to, simultaneously optimize for log P or whatever molecular property while also considering synthetic complexity?
Yeah, so there have been a number of heuristics proposed, including by us, to try to approximate synthetic complexity. And I've gotten really pessimistic about these heuristics. So it is true that they correlate sometimes with the number of reaction steps that it takes to make a molecule, but they really do not understand the subtleties of synthesis and the availability of building blocks that really strongly influences whether you can actually make something. I think I accidentally deleted this backup slide because of course I did, but you can have very similar molecular structures, right, whose synthetic accessibility is quite different by virtue of starting material availability. We can look at these top ones. It's like ribavirin on the left. You make it in one step, super cheap, super easy. The molecule on the right, is not ribavirin. It only differs in the position of that substitution. But because of that, it takes many, many more steps to reach this molecule. It's not, I don't think it's even reported in Reaccess or SciFinder. So these heuristics like the SC score or the SA score can't really tell these apart meaningfully. And so I think there's not much of a substitute for a proper synthesis planning oracle that does the explicit retrosynthesis.
Got it, thanks.
And I have to say, I've gone very weary of all these synthetic accessibility complexity scores. Honestly, so we did a benchmark study recently, and it's in a master thesis. They're basically given completely contradictory results. And so what's the point of having these scores when they basically tell you opposite things? All right, so our next question is by Adrian. You have to unmute yourself.
Yes, I'm mute myself. I'm new to Zoom. I haven't been, only 2 years, right? So, Conor, fantastic. So I have a question again about the synthesizability score, right? It's, do we run the risk of putting ourselves into a corner where, something, I like to believe that there's organic chemists out there that if you show them something hard, they will go like, I take that as a challenge and I will make it happen, right? Yeah. So if we filter by things we know, are we closing some doors, or I'm just curious about your thoughts on that.
Yep, absolutely. So certainly, if we're trying to construct, if we're proposing molecules only using robust reactions that we know will work, we absolutely run the risk of limiting our chemical space. So this does open up a couple of questions. So one is, what is the goal? Is the goal to make a certain structure, or is the goal to achieve a certain function? It could be the case that there exists a molecule within the chemical space we can access that is good enough. Okay. But that's maybe, who knows in advance. If we're talking about integration with autonomous platforms, we might want to be a little bit more conservative in terms of the chemical space we can access. But you're absolutely right. If if we have a computational design workflow that proposes a very large complex structure, right? So for example, if I trusted docking, right, which is the biggest if I think I've ever made, if I trusted docking, right, maybe I would say, well, 0.97 versus 0.94 if I get some validation from another program. If I decide it's worth to make this molecule, I'm sure I can find a chemist who, yes, exactly, will take it as a challenge, or a CRO will take my money and try to make it. But I would argue that we're almost never that confident in our predictions. So I'm very interested in, and this is sort of a forward-looking thing, right? If I'm confident that it's good, maybe it's worth the expense of synthesis. But if I'm not confident, maybe I should stick with the simple stuff.
Right.
And how do we actually balance that? I think it's a really interesting experimental design question, right?
Yep.
But I think for like all of these for de novo design, I would never trust a molecule proposed by a deep generative model enough to do a custom synthesis like this structure.
Okay.
I just think we're not that confident in the predictions. Yeah.
Okay.
All right, so we've got a couple of more minutes for questions. Anyone?
Looks like there's one in the chat.
Oh, okay. Yeah, so do you want to answer that directly?
Yeah, so the question's about recognizing the most relevant fragment in a molecule. How does it work? Is there an attention model? Yes, so essentially by virtue of the parameterization, in particular when we think about message passing networks, we do often have an attention step at the end for aggregation, but even if you use some pooling at the end over the atoms, the model can just flexibly learn to prioritize the important atoms anyway. So you don't actually need an attention mechanism to have this sort of effect of perceiving the most important structures. It's just by virtue of the highly parameterized message update steps that the model can learn to recognize specific functional groups and say, well, if I see an acid chloride, right, I know it's probably going to be reacting in this reaction step.
Okay, thanks. Any more questions? Oh, I'm very glad to hear that, because then I can ask some of my questions. I've got a whole list here. So I'm actually really interested. So you said that so the data which you get to train kind of your scheme comes from Reaxys. Is that right?
Originally, we were using Reaxys. Currently, we are using data from CIS, from SciFinder, as well as Pistachio.
So I mean, so the one thing I'm kind of concerned about these days, and yeah, so again, so what's your thought on publication bias and unbiased biased data sets? And I mean, so Josh Schreier, for example, in his Dark Reactions project, quite nicely showed how important it is to have a properly balanced and unbiased data set in order to make viable predictions. So is that something you ran into in terms of concerns or problems, or what's your take?
Yeah, so definitely having the literature bias towards positive examples influences the types of models we can build. We predict the product of reactions. We never predict 0% conversion. We always predict something, because what's published is something. Now, and I promise this wasn't a planted question, a long-term strategy that we're trying to take to overcome this is trying to create a sort of centralized place to structure and share reaction data that exists in parallel with the traditional publishing mechanisms. So creating a repository where people do share the failed reactions and the negative examples alongside the positive ones. So we work with a nice big team of folks, many of whom think in terms of high throughput screening, where we would expect to have a nice distribution of positive and negative reactions. And we do think this will enable different sorts of predictive chemistry models down the road. So the Open Reaction Database is the name of the effort, where hopefully our launch publication will come out next week. But yeah, this is the long-term strategy to overcome it. In the short term, we just have to ask questions that the data are able to answer.
All right, fair enough. Other questions? Okay, I've got a really quick one. So, I mean, so you make a very nice point for the utility of your approach for, okay, so you have a target molecule and you see, okay, is that doable? What's the retrosynthetic pathway towards that? Have you ever thought about applying that scheme forward in terms of combustion chemistry, for example? Can you do product networks and reaction networks and see what comes out of a combustion with a particular fuel, for example, at particular conditions?
Yeah, absolutely. So that approach of enumeration is frequent in pharma for making make-on-demand libraries and enumerating accessible space. In terms of combustion, that's one of the focuses of my former PhD advisor, Bill Green's work, right? Is a sort of enumerative approach to possible reactions. You need to prune that search space in some manner. So you have to think about the most likely reaction pathways and how to prioritize them to overcome the combinatorial explosion. That's absolutely something that we've thought about. And we've got a proposal in related to using these kinds of techniques for mechanistic elucidation, right? If you have these sort of reaction networks that operate on mechanisms, as others have done, folks like Zimmerman, you can start to understand sort of reactive pathways. And I think Brett also works in this space. So maybe we'll hear about that in 30 seconds or so.
All right, great. So that's a perfect segue. So thanks again, Connor. So that was again a very nice talk. And so our last speaker for this morning is Brett Savoie from Purdue University. And Brett, take it away.
Thank you. So thank you, Connor, also for an excellent talk. You know, it's actually useful to follow Connor, although also intimidating. So even though Connor's just starting out, I think they gave a really phenomenal talk. And regarding generative models, that's what my talk is about. And our approach in this space has actually been quite complementary, I would say. So the summary of the talk is I just want to walk you through one simple idea that we've explored with one of my graduate students here. And since this is a workshop, I've taken the opportunity to present this work in a completely new way. So I've never presented it this way before. And that's the origin of this talk. So more than mimicry. So the question is how you measure learning in these deep generative models, okay? How you measure learning. And sometimes whether you need to do more than mimic, right? So is mimicry good enough sometimes? So if you take some of these molecules to your favorite organic chemist and they like them, does it really matter if the model is just mimicking existing bodies of molecules if it's useful, right? So maybe that's an open-ended philosophical question, but I've never really presented this work in this way. So this is an experiment. So why are we talking about generative chemical models? All right, so in popular culture, generative models are very exciting with respect to, you know, deep fakes, or exciting or scary, depending on your perspective, deep fakes or computer generated music. And you could argue that the forward prediction paradigm, which is what scientists have always done, going from molecules to properties, either through a direct physics-based calculation or through a surrogate model, a neural network or something. This is very efficient, right? So there's been decades of work on high throughput automation of this forward prediction task, trying to go from molecule to some set of properties that you care about. And I would also say that this shouldn't be ruled out, right? So, you know, now you even have some of the people who've been involved with generative models now going back to genetic searches and trying to sort of revisit this forward prediction problem, and oftentimes showing that they can be competitive with or outcompete the generative models. Okay, so the forward prediction paradigm is what we think of historically. The inverse paradigm, I think the earliest example of this in chemistry would be Bertin and Jang's work in the early 2000s. So, and then certainly the most recent explosion of interest in this came from Rafael Gomez-Bombardelli and Alain Asperguzic group. So the idea with the inverse prediction paradigm is that you have the properties that you want, and you try to learn the inverse probability. So rather than finding you know, the probability of properties given a chemical structure or a chemical graph, you're trying to predict the molecules given the property. Now, this is notoriously data intense because this mapping is non-unique. Clearly, there can be many molecules, for instance, that have the same band gap, right? So this is not a unique mapping that you're seeking out. And it can be really difficult to evaluate errors, okay, for all but simple properties. So this is a major issue in contemporary deep chemical modeling, is that we also have a lot of studies that surround a small number of properties that we're trying to optimize against, because oftentimes these are really data intense models. All right, so that's a problem we're going to have to deal with at some point. That's something we've thought a lot about, but I'm not actually going to talk about the data intensity today. So what are the common components of a deep generative model? So you can use adversarial networks. There's also a sort of sub-community that uses adversarial networks for generative modeling. I think that the most common by far, though, in the literature are variational autoencoders. So a variational autoencoder consists of two major components. The first is an encoder, which tries to predict a mean and a variance inside of some latent space. So this is a continuous space. And then you have a decoder, which tries to learn the inverse, tries to go back to molecules. Okay, so at the heart of this thing is that you have this dimensional bottleneck. So it's a compression, right? It's a self-learned compression of chemistry. And the key thing is that it's continuous. So there's been lots of work, which I'm not going to talk about any of this, but as part of a workshop, I wanted to give an overview. So there's been lots of work on how you represent molecules. Connor also gave a nice overview of that. So how you represent the molecules is very important for the performance of these models. There's no doubt about it. We haven't decided to get into that game at all. Okay, so you can choose your favorite representation. There are different advantages and disadvantages for distinct representations. You can also choose your favorite architecture, okay? So, I mean, in principle, you can make an autoencoder out of anything, but, you know, modern autoencoders, oftentimes they have recurrent units, attention mechanisms, but there's a whole zoo of architectures that you can use to make an autoencoder, okay? You can also have multi-component autoencoders, so you can have multiple encoders for different components of molecules or materials, and they can all be feeding into a shared latent space, for instance. Okay, so what have you gotten for this? What have you gotten from this? So this continuous representation, why this is a generative model is that this continuous representation, there's nothing stopping you from sampling it, right? So you can actually take an existing molecule and you can sample around that continuous molecule. So this example is taken from the grammar variational autoencoder from the Hernandez-Lobato group. And this is showing valid decodings starting from a given structure. So they've trained this autoencoder, they've taken this structure shown right here, and they've sampled in the latent space about that structure. And they're showing what happens when you go in different directions inside of that latent space, that you get, you know, a change in the size of the ring, you get more of these branch structures, you get heteroatoms introduced, etc. Okay, so this is the generative aspect. And the question is, what is the quality of these molecules that we're getting out of here? So in about next 15 to 20 minutes, I'm going to highlight some of the challenges of getting good molecules out of this. So one of the things that's preoccupied the community for the past few years is the notion of validity. And you could argue that this is now a solved problem. So there are representations of molecules and neural network architectures that can guarantee validity these days. And I'll come back to what I mean by that. But the challenge is that machine learning is surprisingly versatile when it comes to gaming objective functions. So maybe you've seen these two examples, but I think that these are great illustrations. So back in the early 90s, Carl Sims, published this famous example of a machine learning algorithm gaming a competitive objective function. So he was trying to evolve machines that could walk to a finish line in a simulated environment. And the winner turned out to be this machine, which just falls over because the finish line wasn't positioned far enough away. So the machine learning algorithm had discovered that if it made a very top-heavy machine, it could fall over and cross the finish line, never even had to learn to walk, right? So sometimes the machine learning algorithm can be very good at meeting your objective function, but your objective function doesn't encode what you want to what you really want it to learn, right? A second example, this one is prominent on YouTube. So Tom Murphy trained this greedy AI algorithm to play these Nintendo games. And so its objective function was to avoid dying and to maximize the score. And what happens is that as it gets close to the end of the game, it learned that it could pause. It learned that it could pause. So rather than die, it learned to pause and just indefinitely prolong its life, right? So it's sometimes difficult to encode an objective function, what you mean by good and bad, or what you're actually trying to get these models to do. Okay, so I come from a theoretical chemistry background. And so in density functional theory, there's been this idea of Jacob's ladder that's kind of guided the field for a really long time. And so if I could be so bold, I would say that this is the Jacob's ladder for generative chemical models. Okay, so validity is one problem. So these models don't necessarily know anything about validity, at least in their most naive formalization. So common graph featurizations like smile strings and Inchy strings are very fragile. It's easy to decode to invalid structures. It's easy to decode to things that have invalid Lewis structures like carbon with 5 bonds. So there's many ideas about how to solve this problem. One is you can put validity into the learning formulation. So you can modify your objective function in some way. You can change the representation or the architecture, and these have been very successful. Okay, so there are now representations that decode perfectly. It really solves the validity problem. Or you can always filter afterwards, right? So fine, you generate 1,000 molecules, 90% are invalid, who cares? You can filter at the end. The second problem is stability. So we don't actually have many good surrogates for chemical stability. When I'm wearing a different hat, this is my hobby horse, okay? So methods to predict chemical stability, whether it's acid-base stability, photostability, thermal stability, there's many definitions of stability. I think about that a lot. But when it comes to generative models, we don't have any good surrogates for it to put it into the objective function. Okay, so you can have things that are syntactically valid that just still aren't stable at the end of the day. One idea, which I'm going to share with you all, is that additional property data, even beyond the things you're trying to optimize, might be able to be a backdoor to chemical stability or chemical realism. Another thing that's done in practice is to localize searches about established chemistries. So rather than just trying to optimize over the whole latent space, people routinely do interpolations between molecules or searches about existing molecules. So you're trying to kind of ground your predictions in what you think are realistic molecules. And of course, at the end of the day, you can always filter afterwards, right? So you can show them your favorite chemist and they can filter, they can down select for you. So I would have put synthesizability here, but it didn't fit in my hexagon, so I called it makeability. So this is what our previous speaker has probably been the person who's taken this the most seriously, I would argue, in the field. So, you know, just because it's a valid Lewis structure, and just because, let's say you use some surrogate like heat of formation or something for stability, that doesn't mean you're going to be able to make this thing. That's a smaller chemical space, right? So I would argue, and I think that Connor has basically, I would argue that we don't have many good surrogates for synthesizability. I mainly put that many there because I know Connor has one of the best stability scores or synthetic complexity scores. But we just heard the author of the synthetic complexity score tell us that he doesn't have faith in these scores when it comes to generative models. So maybe we don't have any good surrogates. Okay. So ideas for solving this: update the objective. Okay. So maybe something like what Connor was talking about maybe making your architecture have to be constrained to synthesizable molecules, building that in somehow into either your representation of the molecules or into the architecture itself or the objective function in some way. Limit chemical space. So I'm going to come back to the reaction chef approach, which I think Connor also alluded to. And so the idea here is that we limit our chemical space to things that are plausibly generated from commodity chemicals, or things that we know can be easily produced. Okay, so that kind of circumscribes things at the beginning, and we try to then build a generative model on top of that. Again, we can localize searches about established chemistries, or we can always filter afterward. filtering afterward at some point becomes impractical, right? At some point, you're generating so many bad predictions that it can be impossible to filter, and you may not be generating any useful molecules at the end of the day. And Connor showed a very nice example of that. Even further down the line, formulation. So I put formability here, but I'm really talking about formulation. So I don't work on pharmaceuticals, for instance, but if I did, whether or not something crystallizes or is polymorphic is a major concern in terms of the solubility and the release of drugs in the bloodstream. So that's one example, but the morphology, if I was thinking about polymers, the morphology can be a very important component of the properties you care about. And so I don't think we have any models of that, right? So this is something that is very difficult to model, and we don't have any good surrogates of that. So this is something that, filter afterwards, basically filter afterwards, or localized searches about established chemistries. If you're thinking about getting into this area, I think that this is wide open. Okay, I'd be interested in comments about if people disagree with that. Okay, so in the last 10 minutes here, because I planned this to be about 25 minutes, last 10 minutes, I just want to share with you one idea we had about how we might be able to make more realistic predictions. So our basic idea here is, if we teach models elementary chemistry, then does it improve the overall realism of the molecules that we generate? So if I were to put it in sort of a cheeky fashion, I might say that you have to teach a model chemistry 101 before you want it to start predicting, some binding affinity for an active site, right? So maybe you need to teach elementary chemistry, which it isn't obvious how that relates to your ultimate goal, which is your property of interest, but that can help the model through the back door sort of understand what is a realistic chemistry like, right? What does a realistic chemical graph look like? So the specific architecture that we're going to use is the grammar variational autoencoder. So you can actually use, you can choose an architecture these days that can guarantee validity, but we actually wanted an architecture that still has some invalid molecules that it generates, to see if our idea on its own can increase the validity, okay? Increase the validity of the predictions. So we're going to be using the validity of the predictions as our initial surrogate for how much the model is starting to learn chemistry. And then towards the end of the talk, the second half, I'm going to show some new data we have that also goes beyond even just validity. So what we're going to do is we're going to combine a prediction task like the band gap, which is maybe a quantity that we care about, with some elementary properties like the internal energy or the spatial extent or the 0-point vibrational energy or the heat of formation, which don't have anything in principle to do with the band gap, but they're elementary chemical properties that might help organize the latent space in a way that improves predictions. That's our hypothesis. So can these models actually benefit from learning elementary properties? So let's see what information exchange looks like. So if we were to train on multiple properties, so one of them being the band gap calculated at a semi-empirical level versus the band gap being calculated at the DFT level, these are highly correlated variables. So the first question we wanted to see is, can the model successfully exchange information between these two tasks? So if I just train this model with this extra property prediction, if I just train it on DFT, predict the DFT band gap, this is what the learning curve looks like as we increase the training data set, okay? This is as I start to add XTB data. So XTB is a semi-empirical data for the whole set of compounds. So the semi-empirical data is really cheap to evaluate, right? So I can evaluate all of the semi-empirical data for this whole QM9 data set on the order of 24 hours on a reasonable cluster. And so using that as a learning variable, I can look at what happens as I include more and more and more of it. And what we see is that as we include more and more of the semi-empirical data, the DFT predictions improve in the data scarce regime. So what we're seeing is evidence here of transfer learning. So in this regime down here, there's very few, there's only 10 to 100 DFT examples here, but the model has already learned the difference. Of course, it's only to 0.5 UV, so that's not terrific, but there is definitely a transfer learning effect. So that's what I'm trying to demonstrate here. All right, what if we use two properties that were orthogonal to each other, like the band gap and the spatial extent of the molecule? Well, if I look at the latent space, the model recognizes that these are independent properties and it spontaneously organizes them orthogonal to each other. So these properties that are unrelated to band gap, they don't actually hurt the organization with respect to band gap. It just spontaneously organizes it orthogonal to the band gap. Okay, but this orthogonal organization can still help you if you're sampling about existing molecules. That's the argument, is that by organizing the latent space with respect to these other properties, even uncorrelated properties, it's still teaching the model's still learning something about chemistry. Okay, so here's an illustration of that. This was a toy demonstration where we trained a neural network or trained an autoencoder with only a two-dimensional latent space. And that's because, you know, people get concerned when you show these principal components. So we just wanted to show a two-dimensional latent space. It's not going to be an effective compression because it's just so aggressive, but we can visualize the latent space directly. Okay, so this is an unenriched latent space that we sampled using Savoie sampling, two-dimensional Savoie sampling, to see what is the validity of the structures that we select when we just sample randomly this latent space. So there's no organization with respect to validity. If we look at the baseline validity, I think it was around 15%. Okay, so only 15% of these decoded points on average are decoding to valid molecules. The original autoencoder only decoded about 4% successfully. So these parse trees are a better representation, but still it's not doing a very good job, albeit on a two-dimensional search space. So what happens though if I included, even in this two-dimensional search space, what if I asked it to also predict band gap, also predict internal energy, also predict spatial extent? Well, it's going to have to make a compromise because I have more properties than I have dimensions in my latent space, but I've also sampled and taken a look at what happened to validity. And it's pretty interesting that validity tends to track the structures. So this is being colored according to band gap. So this region right here that has low validity, those are actually negative band gaps. So the model understands, because we've given it a physical property band gap, it knows that there's very few realistic chemistries out here. Likewise, you get to structures that you start losing structures when you sample down here. So there's very few structures because they become too small. And then these structures over here are intermediate sized and the validity goes way up. So this is actually structures that are in relatively low internal energy. So these are small, but they're not vanishingly small like you start to encounter as you move up. Okay, so organization with these secondary properties is sort of a backdoor at teaching your model chemistry. What's a realistic chemistry? So what if we go back to an actual, you know, prediction task that we care about? So we're training these on QM9. So QM9 is small molecules. So we're actually trying to sample in an extrapolative regime of high internal energy, absolute internal energy. So that means we're actually sampling large molecules because above what's represented in the training data. So this is a really challenging extrapolation problem. If you look at the baseline that's just trained on U0, the validity as you extrapolate is only about 4 or 5%. Okay, so it does very poorly trying to extrapolate. But if we give it additional information about 0-point vibrational energy or 0-point vibrational energy and band gap, then this model is actually able to extrapolate U0 with validities up to 40%. Okay, so this is a huge improvement because we taught it something about other chemical properties that filled, we would argue, filled the latent space with more realistic structures. Another extrapolation task here is extrapolating the low band gap structures. So that's also extremely challenging because these are really small molecules in QM9. So there's not a lot of low band gap structures. But if you look at the low band gap extrapolation, it's around 12%. And then once we also train a model on 0-point vibrational energy and internal energy, it jumps up to 25%. If we look at the structures though, so great, 100% diversity, 99% aren't even in QM9. Here's 25 examples. If you ask me, I think we're still getting gamed here, okay? So, I mean, some of these don't look too egregious, but some of these structures, these are the low band gap structures, don't look like they're particularly simple or particularly synthesizable. Okay, so the model is meeting our criteria. These are all validated at the DFT level, these structures and these band gaps, but it still isn't getting at what we would think about when we talk about realism. So we've done a bunch of these experiments showing how different properties impact validity. And there's lots of quantitative, details associated with that. But the general conclusion is that these models do benefit from learning more chemical properties, even if it's off target. We also have recently started coupling this with heat of formation. And heat of formation seems to be a generically very good transfer learning variable for validity. So in just a couple minutes here, I just want to talk about some work that's unpublished and where we're heading with this. Okay, so this molecule chef idea says it takes a very different approach to finding physically relevant molecules. And the idea here is that rather than actually making an autoencoder that's based on the molecules you care about, instead you have an autoencoder that's based on reactant bags or reactants that are synthesizable and accessible. Okay, and then you use as a secondary prediction task, you use a reaction predictor to predict the properties. I'm sorry, to predict the product. So you're indirectly getting at synthesizable molecules by only making an autoencoder that encodes reactant bags that you can access. And then you use a secondary model, I think in this case they used Alpha Lee's molecular transformer in order to take those reactant bags and predict a product, okay? So the idea is that you're constraining that chemical space to be in a physically realistic region. So in the interest of time here, I'm going to just go to this last comparison and finish off here. So what we showed is that if you use this model to predict the band gap, okay, so if we use this model to try to find molecules with a certain band gap, it can select for that band gap. So we were sampling for 6 to 8, and it kind of misses it. This is the distribution, so it gets things as low as 7 or so. But if you look at the distribution of heats of reaction with respect to that bag of reactants, the heats of reaction can be very large. You're talking about things that are up to 400 kilojoules per mole endothermic. So this constraint is actually suffering. It's not actually enforcing the constraint that it was really set out to apply. So if we also include heat of reaction as a learning variable simultaneously, and we try to sample endothermic with respect to the reactants structures, we can move the mean so that on average, the products that we're discovering are exothermic with respect to synthesizable structures. And we've lost, we haven't lost anything in terms of our selectivity for band gap. Okay, so I will wrap it up here with this slide. I think that we're gonna have to deal with this as a community. Are these the best ideas? Almost certainly not, okay? But it's one idea that I thought was unique, this idea of adding some additional property information, that might be a backdoor to more realistic molecules. And so that's what we've pushed forward here. And I want to acknowledge Nick. So all of this work was done by one student who's now at DuPont, and I'm happy to take any questions.
All right, great. Thanks so much, Brett. And I'll open up this talk for questions. All right, there's a question in the chat. Please unmute yourself and you can ask the question directly then. Or if you're too shy, then maybe Brett can answer the question directly.
Yeah, I might have to, how do I bring up the chat while I'm in here?
Okay, so I can ask the question. And so how do you trust structural representations? Do you think some improving with inputting some electronic structure? If yes, how does this happen?
So I'm sorry, how do I trust representing the structures?
Yes.
Okay, yeah, so we have made an unorthodox choice here. So these days, you might argue, why aren't you just using selfies or something that was guaranteed to decode to a valid structure? In this case, we liked the parse trees because they don't give you valid structures all the time. And so we could see how using something that still isn't guaranteed to give you valid structures, does adding additional property data increase the validity of structures? Because there's maybe another perspective, which is that fine, if you use a representation that guarantees validity, the model hasn't necessarily learned what it means to be a physically relevant molecule. And I think that's also what Connor was kind of getting at in terms of it still doesn't know anything about synthesis, even if it's decoding to valid structures, right? I think that quantum chemistry features are going to be very important because these are so data demanding that you need to be able to generate a lot of chemical data to train them. And so that's actually why we've used a ton of additional XTB properties as transfer learning variables. And I think that's a very important part of all of this.
All right, so there was kind of a second part to the question. Does it help to add some electronic structure? And if yes, how does it happen?
Yeah, exactly. So that's what I was getting at with the XTB data. So here's the question: is how many properties should you include here, right? So at some point you might end up trying to optimize things that are mutually exclusive, but in general you're going to need a lot of property data, or you're going to need a good surrogate that you have a lot of. And so we've included a lot of different properties that we can calculate from XTB or heat of reaction. We have a semi-empirical method that we've developed, TCIT, for heat of reaction, and that's where it enters in, is in the property prediction side. If you, on the representation side, if you wanted to use a three-dimensional structure, if you wanted to use the molecular orbitals, maybe, you might be able to also put it into the representation, but that'd be intrinsically more expensive.
Yes, I used to be really excited about combining inherently the quantum chemistry and the machine learning a bit more, but the problem is at the end of the day that creates the bottleneck for everything you're doing, right? So if you have to featureize using quantum chemistry data, then your machine learning model is never going to be faster than quantum chemistry because you need that part for the featureization. So I personally think on that side, it's kind of a dead end. But that's just my personal opinion. Okay, so there's another question about the software you're using for the property generation for the softwares.
Yes, so we really like, well, it's Stefan Grimma's group has developed this GFN2 XTB package, and so that's a semi-empirical, methodology for generating approximate quantum chemistry data, similar to what you would get from DFT, right? But it's not nearly as accurate. So underlying all of this is this data generation issue. And so we've been using the XTB package to generate, hundreds of thousands of properties that don't exist in QM9, for instance, because it's just too expensive for us to recalculate all of those using DFT. So XTB is really important behind the scenes for generating all of our training data. And then I would also point out, so heat of formation, this TCIT method, my student has worked pretty hard on. I would say that this is an outstanding method for really G4 level accuracy heat of formation predictions. So that's how we're generating all of the heat of formation. And there's a GitHub implementation, and it's actually about to be updated as well.
Okay, let me interrupt. Why don't we call this the official end of workshop, and then let me stop recording. And thank you for all for attending and for all the speakers for the great talk.